We need to, having just a trapezoidal map does not guarantee this, because your vertical slabs are not, they do not extend all the way up, so you cannot perform a search on the X and then on Y independently. So in addition to the trapezoidal map we construct, we need a search structure, like a binary search tree, in order to locate, given a point, which trapezoid this point is contained in. And this is, so when we are building, so this is our trapezoidal map. When we are building this trapezoidal map, what we are building is actually this search structure, which is going to support point queries. And the search structure is a directed acyclic graph, is not necessarily a tree, because we are going to see some nodes may have multiple paths that lead to them. And there are, in this search structure, so this is an example search structure for this trapezoidal map. The trapezoids appear at the leaves of this search structure. So there is a unique leaf for each trapezoid. And the intermediate nodes are of two types. They can either be points or segments. The point internal nodes are called X nodes. I think it was they were called, yeah. X, if it contains a point, we call it X node. If it contains a segment, we call those internal nodes Y nodes. And the reason the X and Y is actually very intuitive. When we come to a point, we compare the X coordinate of our query point with this point. Okay? And based on that X coordinate, we either go left or right. For example, if our query point lies to the left of P1, I know that it's in trapezoid A. Okay? So this is P1. So P1, Q1, P2, Q2 are the endpoints of the original line segments, which are non-intersecting. So here we perform, when we end up in a leaf, it means that our query point is contained in that trapezoid. So, and this is not like levels in KD trees. We are not alternating or such, okay? So it's really the X and Y nodes can arbitrarily be in different places. But their main purpose is each X node allows us either to go left or right of that point. For example, when we are at P2, when we compare at P2, if our query point's X coordinate is to the right of P2, we know that that point is going to be in one of these trapezoids. It can even be in trapezoid B, okay? Because B also, the point, our query point may be here. So, but all the trapezoids who are strictly to the left of this point P2 is filtered out during this search. Now, imagine I'm searching something here. This is my query point Q. Okay, so this is what we do. Q, we compare its X coordinate. It's greater, so we go right. And then we come to Q1, we come to this node, we compare its X coordinate. Again, its X coordinate is greater than Q1, this Q's X coordinate. So again, we go right. Okay, then we go to Q2. We see that its coordinate is smaller, so we go to this Y node. At Y nodes, we have segments. And when we come to Y node, we guarantee that this is that segment. What we ask is, the query now we ask is, does Q lie below or above this segment? And when we come to a Y node, in order to answer such questions correctly, we need to guarantee that this segment and Q are, a vertical extension on this Q intersects this segment. Okay, the segments S2's X and Y, the X coordinates of its endpoints encapsulate the X coordinate of Q. So we can uniquely say that Q either lies below or above this segment. Okay, and when we come to S2 here, we ask this question: does Q lie below or above? It lies below. So if below is right child, above is left child. So if Q was above, it will be trapezoid E, otherwise it's trapezoid F. So this is each of them it's a binary directed acyclic graph. This with binary. So E, if it was lying above, we would end up at trapezoid B. Since it's lying below, we end up at this leaf F, which is this trapezoid. So we could have come to this F also. So we come to this. So we followed. So this trapezoid F actually virtually is divided into two regions. If my point was in this region, I would have followed a different path to reach the same trapezoid. In that case, I would have, from this Q1, I would have taken the left path because it's axis. So the same trapezoid F can be reached from two different paths, therefore it's not a tree. Okay? The search structure is not a tree because different query points may end up at the same leaf by following different paths on the search structure. Okay, so this is our search structure. It has points and segments. At points, we compare their x coordinates, and at segments, we just check whether the query point is above or below that segment, and this search is going to lead us to the trapezoid we are looking for. Now, the question is, this search time, is it going to always guarantee log n? Unfortunately not. I mean, if you have an unbalanced tree, we may end up having paths of, having a trapezoidal map with a very unbalanced structure, and the path length may be on the order of ON in the worst case. And therefore, again, to find the actual running time complexity, we need to, when we are constructing this tree, unfortunately, the incremental approach, the order of segments inserted in this tree is going to determine the structure. So the order of these segments are going to give you different orders, are going to give you different structures. So why do we say randomized incremental algorithm is that we are going to start with a random permutation, a random permutation of these segments. We are going to randomize these segments given to us. We are going to process them in a random order. And at the end, the running time complexity analysis is very complex. So I'm not going to talk about the running time complexity analysis in detail in this class. But the expected running time, in order to find expected running time, we need to, again, going to think about probability of adding new nodes. We need to look at the geometry and see what is the probability of having an unbalanced structure here or balanced structure. And at the end, we are going to see that a randomized permutation gives us an expected running time of log n. Okay, so if they are not sorted in a certain order, your segments, you are probably going to get, on average, expected running time is going to be, expected tree is going to be a balanced tree, and you are going to have log n expected query time. So how do we construct this tree? So we start with an empty structure with no nodes in it and with no segments. We are going to process our line segments one by one, and each time we are adding a segment, we are going to update our structure. Now let's start with the general description of the algorithm, how we update this. Okay, I'm going to erase this and draw. So what happens? What do we need to update? So let's first discuss what do we need to update when we insert a segment. Which part of the structure changes? Okay, so we need to first think about this. Imagine we have an existing set of trapezoids. Okay, so these are the two line segments. This is the other line segment, and I have let's have this shorter, and what I'm going to have here is that. Okay, these are my linear extensions. So these are, I'm going to name them delta 0, delta 1. So these are my existing trapezoids, delta 2. Okay, so these are my, oh actually in the example I had another line segment, possibly non-intersect. I can, so this is again an existing line segment here. These are the vertical extensions. Okay, now, okay, delta 2, delta 3, delta 4, delta 5, delta 6. Now, here, let's insert, so this is my existing previously processed line segments, and imagine we add this line segment Si at the ith iteration. So we are going to do an incremental approach. We have inserted the first I-1 segments into the trapezoidal map and constructed a structure for that. And we are inserting this ith segment here, and the ith segment is this. Now, what will happen is that when we introduce this ith segment, we are going to have these extensions. Okay, we are going to add these extensions. And the trapezoids here, and these delta 1 is sliced into 2, delta 2 is sliced into 2, delta 3 is sliced into 2, but there is no change in delta 6, right? Nothing has changed in delta 6. Delta 4 is sliced into 2, and delta 5 here is sliced into three pieces. So, but the thing is, the rest of the map, if there was other trapezoids in other places, will be unchanged. Okay, we don't need to. The part that we need to update are the trapezoids that intersects with this newly inserted line segment Si. So here is the algorithm. When we insert a new segment, we first find the sequence of trapezoids, the set of trapezoids that are properly intersected by this line segment. So this is the overall description. First, find all the trapezoids that are intersected by this segment. And then remove them, since they are going to be updated, they are going to be changed. Remove all these intersected segments from the existing tree. And okay, and replace them the new trapezoids that appear because of the new segment. The new segment is going to introduce new trapezoids, and we are going to remove delta 0, delta 1, delta 2, delta 3, delta 4, delta 5 from the tree and add new trapezoids into the tree. So this is the general description of the algorithm. Okay. We may need to, during this insertion and removal, we are going to, when we are updating this tree, we are not only removing the leaves are going to be removed, but during that removal, some internal nodes may also need to be updated. Some internal nodes may be removed or they may be updated as well. Okay, so for example, first of all, we are inserting two, so PSI and QSI, the two endpoints of the segment Si is going to be inserted as internal nodes. Okay, they are going to be new X nodes that are going to be inserted into the tree. And the segment Si itself is going to be inserted as an Y node, Y internal node. So we are going to be inserting, in addition to the leaves, in addition to the trapezoids we are also inserting some intermediate nodes in the tree. But the important thing here is that the only thing we need to update is the trapezoids that intersects with the segment Si. Now, how do we find these trapezoids? So during this construction, so one process that we need to do efficiently is, given a segment, find the trapezoids, the sequence of trapezoids intersected by it. So in other words, delta 0, delta 1, delta 2, delta 3, delta 4, delta 5. How do we find them? The good thing about this finding is that we know that we have a search structure up to now since we inserted the first S-1 segments, and during this insertion, we build a search structure which is valid, what I can do is, I can efficiently find, for example, which trapezoid the beginning point of SI is contained in. Okay? I can conduct a search on the already intermediate search structure to find delta 0. So delta 0 can be found easily by a point query on the existing structure. Okay? So you search for PSI on the structure that you have constructed up to step Si-1, up to step I-1. So you locate delta 0. Now, if we know delta 0, can we find the sequence of trapezoids that are intersected? I mean, can we find delta 1, delta 2 again efficiently? And in the book, there's an algorithm which says the follow segment algorithm. So this is our segment SI. We can, the good thing here is that if after we have delta 0, we uniquely, it has at most two neighbors, right? Two right neighbors. Imagine this case. This is a delta 0. It may possibly have two right neighbors. Okay, so this is delta 1, delta 2, for example. Now, the delta 0 possibly have two neighbors, or it may also have, if it degenerates to a point, okay, so this is delta 0. Actually, at this point, it's going to have a unique right neighbor. The right neighbor of this is going to be a unique, even if it's like this, since we do not allow multiple endpoints to end at the same point, so it's going to have there's going to be a unique delta 1 at this point. So just let's consider this case. In this case, what we need to do is, based on where our segment is, okay, this is our segment. If this was our segment that's newly inserted, the next segment, the next trapezoid after delta 0 should be delta 2. And we can find this easily by checking the right P of delta 0. Imagine, remember, we store 4 things for each trapezoid. Its top segment, its bottom segment, its left point, and its right point. Okay? So these are the 4 things we store for each trapezoid. So this right point is available to us. By comparing this right point with the newly inserted segment, we can find which of these neighbors, either the upper neighbor, upper right neighbor, or lower right neighbor, will be the next segment to be inserted. So we follow these trapezoids until we reach the right endpoint of the newly inserted segment. So in log n time, we find this PSI, expected log n time, we find the initial trapezoid that is intersected, and by following the trapezoids along the segment, we find a sequence of trapezoids that are intersected by this segment. Okay, so we can, one step of the algorithm, finding all the trapezoids that are intersected by the newly segment, can be done efficiently using this approach. Okay, is it clear? Now, the remaining thing, I mean, in order to complete the construction algorithm, now we need to discuss, okay, after you found this, how do you modify the search structure? So how is this search structure modified with the insertion of this new segment? And I'm going to first show us an easy case when the segment is contained in a single trapezoid, what we do. And then the general case is also going to be easier to describe after this. So here, let's assume this is our trapezoid. Okay. So yeah, let's have it. This is the end. This is one of the endpoints. And let's assume SI is fully contained in an existing trapezoid let's name it delta, for example. Okay, so P1 and Q, yeah, let's name them PI and QI. Okay, now, before we insert SI, this was our search structure. So whatever it was, so this is our search structure D. There was a single trapezoid delta, which was a leaf in this search structure. So before inserting SI, our search structure was this. Now, what will happen when we insert this SI? This is the part that we are going to modify. So first of all, we need to erase this part. The delta is no longer going to be there. It's going to be replaced with, so look at these extensions. Let's A, B, C, D. Let me use the same thing. And the search structure is going to be something like this. So the existing part, we don't touch that. And we can add the X node PI, QI, SI, and it's going to be B, A, C, and D. Okay, so if I replace that leaf node with this new subtree like this, I'm going to have a valid structure for the because at this point I ended up, if I'm at this point during this path, I know that I'm in this trapezoid. Now all I need to do is, if I know the point is in this large trapezoid, the search structure that I need to add is that which one of these 4 subtrapezoids, A, B, C, D, the point is in. So all I need to do is to add that subtree that supports this finding which of these 4 subregions the query is located in. And it can be done, this is not a unique tree, by the way. You can, for example, first look at QI, then PI. I mean, this is not a unique way to modify the tree. I mean, there is no reason why we look at PI's X before QI's X. You could do something reverse, okay? But this structure is going to allow you, by looking at PI, if its X coordinate is smaller than PI, it's in this A trapezoid. If it is X coordinate is larger than QI, it's in this B trapezoid. Otherwise, it's in this region. To find whether it's either in C or D, I compare it with SI, and based on that, I decide it's in C or D. Okay, so modifying the study structure like this, we are able to insert a new segment and update the search structure. Now, this is the easy case when our segment is contained in a single trapezoid. So what happens when we insert in a, now I'm going to talk about a more general case, and but the modifications are going to be a little bit more complex, but still we'll be able to do modifications in linear time, or not linear, in constant time actually, because since we can access the neighbors of these top, bottom, left, right of each of these trapezoids in constant time, we'll be able to do it in constant time. So what the search is going to be, since the main dominating complexity will be to find which trapezoids the segments are intersecting with. So this initial cost, finding the sequence of segments that are intersected by the new segment, is going to be the dominating part in this algorithm, so which is going to take log n time. And since we do n insertions of these segments, the total complexity of the construction is going to be n log n. The expected running time. Okay, so if we don't have a balanced tree, in the worst case, it may be n squared construction time with ON search. So is this clear how we modify the search structure? Now, in the general case, so in this example, I have 4 segments that are intersected by SI, and this is an interesting case where SI actually shares a point, an endpoint with previous segments. So here are the existing segments that are already inserted. And these are their extensions. And the extension of this. So here is my newly inserted segment. This is PI, and this is QI. So this is segment SI. And these are the trapezoids that are intersected. So this is delta 0, delta 1, delta 2, delta 3. Okay? And in the original structure, D, each of these delta 0, delta 1, and delta 2 appear as leaf nodes. Now, in the algorithm, what I do is I remove these leaf nodes first. So these trapezoids are going to be changed, okay? The trapezoids are going to be changed, and I'm going to add new trapezoids. And they are going to be like this. The extension, the previous extension of this point, for example, now is going to end here, okay? Because it's going to be intersecting segment SI, so it's going to, that extension is going to end here. And also the lower extension of this point is going to end here since it's intersecting with SI. And the other thing, I'm going to have extensions here, the new extensions. It's just QI. So I have, so this was delta 0 initially. Now the new segments that I'm writing are these. I'm deleting these, C, D. And again, this is going to end there, the lower extension, E and F. Okay, so these are the new segments that I'm going to insert. And they can be, the new structure is going to be okay, so this is going to be the new structure. As you can see, I use SI multiple times. The same internal node may be used multiple times, and there may be multiple paths. But each of these paths we do not add new paths here. These are all, since it was intersecting with 4 trapezoids previously, these are the search that end at these trapezoids. And since I'm going to refine these trapezoids with the introduction of this SI, so what happens is that when we introduce this SI here, the existing trapezoids are either divided into multiple trapezoids, or sometimes they may be merged into a single trapezoid. But the thing is, I don't want to change the previous part of the search structure. So I need to take care of, for all these trapezoids, a search that ends this trapezoid. How am I going to refine it? So I need to solve this in order to properly update the search structure. For example, if you were previously, so it's bad that I removed, I deleted delta 0. So delta 0 was this. So let me write it here again. So this triangle was delta 0, right? So a search that was ending at delta 0 now ends at this path, okay? But now what you need to do is, part of this triangle belongs to trapezoid A and part of it belongs to B. So we need to add the necessary search structure to be able to distinguish between part A and part B. And what is going to help us in that regard is this line segment, okay? SI determines whether we are at A or B. For some, we don't need to insert Q here, because any point within here is going to have the same X interval, okay? These two trapezoids, up and down trapezoids, A and B, this part of A and this part of B, is not distinguished with respect to their X coordinates. They are distinguished with respect to this line segment. Therefore, we add this line segment here. So if it is above the line segment, it belongs to trapezoid A. Otherwise, it belongs to trapezoid B. So this is the path that was ending at delta 0. The path that's ending at delta 1, now part of it belongs to, again, A. Okay, so delta 1 was this one. Okay, so this was the whole thing here was delta 1. Now again, delta 1 is divided into 2 regions, A and C. And again, I can distinguish between 2 regions by looking again at SI. So SI, the Y node is inserted there. Same thing for delta 2. Delta 2 was again cut by SI into 2 regions, C and D. So delta 2, the search that ended at delta 2, again distinguish between D and C. And here, this part, the endpoint QI also divides the delta 3, the search that ended at delta 3. Delta 3 was this big triangle, okay? This QI appears as a midpoint. So if a point appears to the left or right of this point, we need to distinguish that this is going to distinguish between these two trapezoids, E and F. So therefore, we look at QI first. If it's right to the QI, it's F. If it's to the left of QI, again, since there are 2 trapezoids, it can be either E or C. We have to look at which segment it is contained in. Okay, so for each trapezoid, old trapezoid, we end the search in that trapezoid, and all these new edit search structures are about how to refine this new trapezoid. This new trapezoid, is it divided into 2 regions, up and down, or is it divided into 3 regions from left or right? But the important thing is here is that this newly added search structures is constant space, because of the fact that each trapezoid has 4 neighbors, we can at most divide with this line segment, can divide an existing trapezoid into 2, or if it is an endpoint in that trapezoid, it may at most be 3 trapezoids. So can it be 4 trapezoids? No, I mean, at most 3 trapezoids at the end, I guess, because I mean the individual search structures we are going to add at the end of each search path can have at most 2 leaf nodes, or at most 3 leaf nodes like this. and therefore we are going to compare either on two x and y nodes. So we are adding constant space for each of these trapezoids, but the number of trapezoids we are intersecting can be large. Okay, so if we are intersecting n trapezoids, we are going to have n such search structures. So the update may be costly, but the expected running time is that the newly inserted segment is not going to be intersecting many trapezoids in the expected manner. It's just going to intersect a number of them, and this is how we update. All these updates can be done by making use of the existing information and the newly added segment. Because, for example, for this trapezoid, in order to find where, we don't need to actually store these intersection points. These are all symbols. We already know the top of this trapezoid and the bottom of this trapezoid. Okay, so when we add these new trapezoids, E, C, and F, their bottom top fields can be updated easily, since we already know these fields for the existing trapezoids. So, and we don't need a doubly connected edge list for the trapezoidal map. For the N or ON trapezoids, all we need are these 4 fields. Okay, so we don't need the vertex edge records. All we need is what is the top segment, what is the bottom segment, what is the left point and right point. So after storing these for each trapezoid, and with the help of the search structure, we can locate any point in any subdivision efficiently. So the final conclusion is that we construct this structure in ON log n expected time, and its expected size of the search structure is ON, linear, and the expected query time is O log n. Okay, so that's it for today, and your assignment is something different than trapezoidal map. Actually, it's just